had snoozed too many times, and he just never looked at me. He was like, he wasn't amused by it.
No.
I try to make him laugh, and he didn't laugh.
He has no sense of humor. Well, actually, he does, but it's very rare.
I was working. He lied, because I always lie.
I was busy.
Morning, Dr. Gobb. No, I'm not. The heck you talking
Yeah,
about?
the one time I've seen him like laugh was Sydney had 2 coffees. She had gotten one for me and one for herself. He comes in and he goes, "Are you trying to tell me something that you need 2 coffees to stay awake during the class?" He's like, "Where should I leave it?" And I said, "Well, I'm in there with her."
And she's having food. And I was like, yeah, so there's nothing to it around 6 You're gonna make her not come back.
You still are late.
The concrete's on your door.
In the mailbox.
Oh, my mailbox, yeah. That's all.
Where at?
They already fired it before you got there.
They're never there. Ever. That's where I've been from this summer. Put it in their mailbox. No. Maybe Rick Holiday.
Mr. Seelig.
Hey,
Oh, John.
you don't think that he's still accepting that ACL this month? I know it says due the 30th.
I give it to him.
But, okay, I didn't think that.
John, I like him.
He was really nice.
No, I didn't even get it. I just actually,
So, what chapters are our tests going to be over this week?
For what? For structures?
Yeah. Like, what class are we in? Don't confuse me like that.
Because you're taking concrete, right?
Yes.
But this week, actually. Okay, so what do you mean, what type of questions?
No, what chapters?
What chapters? Just the slope deflection. We didn't cover anything other than the slope
So,
deflection.
just chapter 11.
so did it get moved next week?
Yes. Next Thursday.
Yeah.
Why didn't I think about email?
I sent an email to everyone about the test, right?
Yeah, saying if you didn't hear back from him, it's moved.
Oh, I didn't read that much of it.
Didn't actually read it, but
I just
I'm
thought.
going to go ahead and put in my 2 cents anyway. I saw that.
You want to read his email?
I am.
I'm not good.
Well, they were offering it when I had to go get my Hefe, and I'm like, well, you're not going to get me down here again. So, yes. Well, we're required to get Hefe now at the restaurant. And they're, yeah. So, they're like, you want food? I'm like, might as well get me both on. Get out of here. I got water.
Okay, so good morning, everyone. We're gonna go back, continue our discussion about the slope deflection method for frames. So first we covered beams, now we're covering frames. So frames can have side sway unless there is something prevented this frame from having a side sway. What we discussed last time, we had this frame over here. This is the example that we solved last time. Okay? So would this frame have a side sway like this or not? It didn't. Why? What prevented this frame from having a side sway? The symmetry, okay? So symmetric frames doesn't have side sway, okay? So is there anything else that would prevent, let's say you don't have a symmetric frame, would it have a side sway or not, okay? So let's see an example now. This is example 11.6 that we're going to solve and see in this problem, for example, would it have a side sway or not? Okay, so without seeing what loads are applied, okay? This is point A, B, C, D, and E, okay? The dimensions, let's write the dimensions here. 2.4 meters, 2.4 meters, 3.6, and 4.5 meters. For a frame like this, would it have a side sway? Not. It's not symmetric, right? It's not symmetric. So if it's gonna have if it's not gonna have a side sway, not because of symmetry, okay? So the question now, would it have side sway? Can it sway to the right or to the left or not? No, why not? Yes, pin up here. That means that point E cannot move horizontally. And point E is connected to point C through this member. That means that point C cannot move horizontally. The point C is connected to point B through this member. That means that point B cannot move horizontally. Okay? And the points on the lower side here, A and D, they are fixed and pinned, so they cannot move horizontally as well. So this level cannot move, this level cannot move, so there is no side sway, okay? Regardless of what loads do you have. Let's say, okay, don't draw this, okay, this is not the problem that we're gonna solve, but let's say I give you like the same problem on the test, okay? But I just changed this to roller support. Would it have a side sway or not? Yes, it's a completely different problem. There will be another degree of freedom, which is the side sway, if this changes to a roller support. But just having it as a pinned support, it prevents the side sway here. So now what are the loads applied on this frame? Here we have a uniformly distributed load of 50 kilonewtons per meter, okay? And here, right in the middle of member BC, there is a force of 30 kilonewtons. I didn't name this point, but you can name it as F, for example, okay? So let's say on the test I don't name the point for you, just name it, okay? No, there is no problem, okay? Give it a name, point F, okay? And now for this frame, okay, the sizes of those members are not the same, okay? They have different sizes. So what does this mean? That the moment of inertia of each member is different. So the moment of inertia for this member AB is 160 times 10 to the power 6 millimeter power 4. The moment of inertia for this member is 320 times 10 to the power 6 millimeter to the power 4. For this member, it's 80 times 10 to the power 6 millimeter power 4. This member, 260 times 10 to the power 6 millimeter power 4. Each member has a different section, okay? So the moment of inertia of each member, okay, is different. Okay? The E, the modulus of elasticity for the material used for this, is 200 gigapascals. What material do you know has a modulus of elasticity in that range? Does anyone know? Steel. Okay. So maybe this is a steel structure, okay? The modulus of elasticity is 200 gigapascals here, okay? The exact value for steel is 209, okay? But approximately 200 gigapascals, okay? The moment of inertia is given for each member, okay? So what we're required to do here is to draw the bending moment diagram for this thing, okay? So how can we proceed to solve this problem? Rate the beam. So I don't want you on the test to, waste your time. Just follow the steps as quick as possible. The first step, break the structure into the individual members composing it, and do what when you break it? Find the degrees of freedom, the rotations, the deflections that are allowed at each end. Okay? So here we have this member, AB, BC. You have to break it at point C. Okay? CD, and then CE. How much is theta A? Let's write the thetas at each end. Okay? Theta A, how much? 0. Is there a theta B? Yes, it's unknown, which is the same value here. Okay? Theta C here, is it known? It's unknown. There is a theta C. There is nothing preventing point C from rotating. And point C is shared between those three members, so it's the same theta C. Okay? What about theta D? Unknown, right? Do you need to know how much is theta D? No. Why not? Because you know that the moment at point B is 0. So what does this mean? If you know that the moment at point B is 0, you're going to use the modified equation for member CD. Okay? So you don't need theta D. Okay? So I'm not going to write theta D equals 0. Theta D is not 0. Okay? Never write this. If you do write theta D equals 0, you're going to lose a lot of points. Okay? Not just 1 point or 2 points. You're going to lose a lot of points because theta D is not 0. Okay? And then theta E. What about theta E? It's not 0, but I don't need to know how much is theta E if I use the modified equation for member CE. Yes?
Just clarify, they're not needed because it's assumed 0 because of the pin?
Yes, when you have a pin support at the end, so the moment, you know that the moment is 0 at that point. So once you know that the moment at one end of a member is 0, you can use the modified equation. The modified equation excludes the rotation at that point. Okay, you don't need to know. Okay, if you use the modified equation. So now, what about the deltas? Is there any delta here for member AB? Can it have any delta? Can it move like this, or the lower point move horizontally? No. So delta here is how much? 0. For member BC, it's horizontal, so delta is a vertical. Can member B or member C, point C, move upward or downwards? No, because point B is connected to point A, which is fixed, so point A cannot move vertically, so point B cannot move vertically as well. So delta here is equal to 0 as well. And the same for member CD, it cannot move horizontally at point C or point D. And for CE as well, point E cannot move vertically and point C cannot move vertically. So those members, there are no deltas at all. So what are the degrees of freedom here? What are the kinematic degrees of freedom? How many? 2. So the kinematic degrees of freedom, I have 2 unknowns, which are theta B and theta C. That means that later on I'm going to need 2 equations of equilibrium. Okay? Now, what's the second step? Write the fixed end moments. So how many members do we have? We have member AB. What are the fixed end moments in AB? AB and BA. Member AB, what are the fixed end moments? The fixed end moments comes from the table at the back of your book. due to the applied loads. What are the loads applied on member AB? 0. There are no loads applied on member AB, right? Is there any load here? No. So the fixed end moments are 0. What about member CD? 0, right? Member BC, will there be some fixed end moments here and here? How much? Just look at the back of your book. You have a load right in the middle. How much is this? We derived this by hand, by the way. It's at the back of your book, but we derived it by hand. PL over 8. Okay? For a concentrated force in the middle, it's PL over 8. What about this member? WL square over 12. But this, we just said the moment here is 0. So you're going to use the modified equation. So you're looking for the modified fixed end moment, which is on the right side of the table at the back of the book. How much is that? WL square over 8, not WL square over 12. Okay? So let's write those fixed end moments then. So the fixed end moments AB is equal to the fixed end moment of BA is equal to the fixed end moment of CD is equal to 0. While for member BC, we had a force right in the middle that is equal to 30 kilonewtons. So those are the fixed end moments. So the fixed end moment of BC is equal to, is that positive or negative? Is it clockwise or counterclockwise? Counterclockwise is positive or negative according to the sign rule for the slope deflection method? Negative. So negative PL over 8. So negative P is 30 kilonewtons. L is 4.8 meters divided by 8. So the fixed end moment is negative 18 kilonewtons meter. What about the fixed end moment at the other end of the member, CB? It's the same value, right? PL over 8 as well, but it's positive because it's clockwise, right? So 18 kilonewtons meter, not negative 18, positive 18. And then we have the other member, member CE. On member CE, you have a uniform load of an intensity of 50 kilonewtons per meter. The length of CE is 3.6 meters. What are the fixed end moments? So here we have a fixed end moment of W L squared, okay, over 8. So the fixed end moment of CE, but this is the modified value, okay? Is it recording still? Okay. So this is negative WL squared divided by 8, so negative W is 50 kilonewtons per meter times the length squared divided by 8. So the fixed end moment for CE, okay, is negative 81 kilonewtons meter. Now, what's the next step? I found the fixed end moments. What should I do next? Write the slope, deflection equations. How many equations will I write here? How many members do you have? 4 members, right? 1, 2, 3, 4. You write the slope deflection at the both ends of each member, right? So how many equations will you have? 8? To modify. So you're not going to write the equation here or here. So that means that you're going to write it 6 times. Okay? You're going to write the slope deflection equation 6 times. 2 for member A, B, and B, C, and 1 for member C, D, and 1 for member C. Okay? So let's write the slope deflection equations. Let's start by member AB. So MAB, the moments at the two ends. MAB, what's MAB? 4EI divided by L multiplied by theta A. How much is theta A? 0. Plus 2EI divided by L multiplied by theta B. Right? Minus 6EI divided by L squared delta. How much is delta? 0. Plus the fixed end moment of AB. 0. Okay? So here we have 2 EI. E was 200 gigapascals, right? 200 gigapascals. So 200 gigapascals, okay? I'm going to multiply this by 1,000, okay? And then I. How much is I? How much is I? 160 times 10 to the power 6 millimeter power 4, which is 160 times 10 to the power negative 6 meter to the power 4. Okay? So what did I do here? I changed this gigapascal from gigapascal. Gigapascal is 10 to the power 9, right? Pascals, which is Newton meter. Okay? Newton per meter square. Okay? So I guess no. Here I have to divide by 1,000 to change from gigapascal, okay, to sorry. So I have to multiply by 10 to the power 6. We did this before. 1 gigapascal. Just to explain this, 1 gigapascal is equal to 10 to the power 9 pascal, right? And 10 to the power 9 pascal, it's Newton per meter square. So this is 10 to the power 6 kilonewton per meter square. So I have to multiply by 10 to the power 6 to change gigapascal to kilonewtons per meter square, so that I have consistent units. Okay? And then I changed I from millimeter to the power 4 to meter to the power 6. So I divided by 10 to the power negative. I divided by 10 to the power 12. So changed from 10 to the power 6 to 10 to the power negative 6. Okay? And then I divide by L, the length. How much was the length? 4.5 meters of member AB. Okay? So now, this is equation 1. And then you do the same for MBA. For MBA, what's the equation? 4EI divided by L theta B plus 2EI divided by L theta A, which is 0, minus 6EI divided by L squared delta, which is 0, plus the fixed end moment of BA, which is 0. Okay? Just substitute the value of E, the value of I, the value of L, as we did, and then this is equation 2. Okay? Hmm?
We need a theta B in equation 1 there.
Yes. There is a theta B here. All of this is just 2EI divided by L. 2EI divided by L theta B. Okay? So MAB and MBA. Now we go ahead and write the slope deflection equations for member BC. So for member BC, we use the regular equations, regular slope deflection equations, or the modified one. BC. Regular, because the moment at point B is unknown, the moment at point C is unknown. Okay? So here, MBC and MCB. Okay? MBC is how much? 4 EI divided by L. Okay? You have to make sure you use the correct I. Okay? I for that member and L for member BC multiplied by theta B plus 2 EI divided by L theta C minus 6 EI divided by L squared delta. How much is delta? 0. Plus the fixed end moment. How much is the fixed end moment? Of BC. Negative 18. And that's equation 3. I just want you to realize that here those I and L is for member AB. This is for member BC, so you have to substitute the correct values here. MCB is 4EI divided by L theta C plus 2 EI divided by L theta B plus the fixed end moment, which is positive 18. That's equation 3. Sorry, equation 4. And then let's move to the next member, okay? Member CE. For member CE, how many slope deflection equation you're going to write? Just one, which is MCE or MEC? MCE. You're going to use what equation? Just tell me what equation. The modified one, which says 3EI divided by L theta C. Yes, minus 3EI over L squared delta. Plus, how much is delta in this member? 0. Plus what? The fixed end moment of CE, not the regular fixed end moment, the modified one. Okay? So here this becomes 3EI divided by L, the length of that member. Okay? The length is 3.6 meters, and I here is for member CE. Okay? Theta C plus the fixed end moment, which was negative 81. And this is equation 5. And then the last member, member CE, member CD, okay? Again, you're just going to write one equation, MCD. Slope, the modified one, the modified equation. So 3EI divided by L theta C plus 3EI divided by L squared delta, delta is 0, plus the fixed end moment modified for CD. How much was that? 0. Okay? So here we have 3EI of member CD divided by the length, which is 4.5 meters, theta C, and that's equation 6. So as you have here the 6 equations, what are the unknowns in the 6 equations? Theta B and theta C. Okay? Those are the unknowns that we have. What's the next step? The equations of equilibrium. So, equations of equilibrium. What were your unknowns? What are the unknowns? Theta B, theta C. That means that the equations of equilibrium. How many equations of equilibrium you're going to need? 2. If theta B is unknown, that means that you need an equation of equilibrium that looks like what? The summation of the moments. But what point? The same point, theta B. So MB is equal to 0. Theta C is unknown. That means that the equation of equilibrium is the summation of the moments at point C is equal to 0. What does this mean? When you broke your structure like this, here, let's throw them in a clockwise direction. You had an MBA. Here you had an MBC, MCB, MCD, MCE, right? And here you had MAB, right? It says that the summation of the moments at point B is equal to 0. Where's point B? Those two moments has to be equal to 0. The summation of them has to be equal to 0. They have to be equal in magnitude and opposite in direction, right? So that's the first equation here. When we say sigma, the moments about point B equal to 0, we have MBA plus MBC equal to 0. Let's name this equation 1. Okay? So you add those up, okay? What you're going to have? You're going to have an equation in two unknowns, theta B, theta C, right? Because MBA is, in terms of theta B, and MBC is in terms of theta B and theta C, okay? So now doing this, okay, here we're going to have 4 E, I is 160 times 10 to the power negative 6, okay, and L was 4.5, theta B, that's MBA, plus 4 E, I was 320 times 10 to the power negative 6 divided by L, which was 4.8 meters, theta B, plus 2 E I, which is 320 times 10 to the power negative 6 divided by L, which is 4.8 minus 80 equal to 0. Now, is there anything wrong that I did here?
Just do a negative sign on that.
Hmm?
Power 6 at the end.
Okay. 10 to the power, okay, the negative here. Okay, so I didn't substitute the magnitude of E. Would that be fine or not?
Yeah.
Yeah, it's just going to cancel, right? Another thing that, I could have made, actually, if you put this as 10 to the power positive 6, would that be correct or not?
Still give the same answer.
Still going to get the same answer, okay? So changing it here from millimeter to meter, it's not going to make a difference because it's going to cancel at the end, right? Just multiplying by a constant and you have 0 here, so it's not going to make any difference, okay? No, sorry, it's going to make a difference, okay? Why? Because you have this value. So if you change it from 10 to the power negative 6, okay, to 10 to the power 6, then you're actually changing this value, okay? You cannot multiply everything here, okay? So this is the first equation. So this is equation 1. And then equation B, you have the moments. This is equation B now. The summation of the moments about point C is equal to 0. What are the moments about point C? Three moments, right? Don't forget this. It's a joint where you have 3 members, so you're going to have 3 moments. The summation of all those 3 moments has to be equal to 0. So here we have MCB, MCE, and MCD. So all starting with C, MCB, MCE, and MCD is equal to 0. That's equation 2, okay? So you just go ahead and substitute the values, okay, of MCB, okay, and MCE and MCD, and then solve the 2 equations together. So now you just solve equation 1 and equation 2. So theta B is equal to 3.124 times 10 to the power negative 5 radians. And theta C is 5.792 times 10 to the power negative 4 radians. So this is the magnitude of the two rotations, theta B and theta C. Okay? Any question here? So now, once you solve for theta B and theta C, what's the next step? This was equation of equilibriums. And then, what would you do? Substitute those values back, okay? Substitute theta B, theta C back into equations 1 to 6. Doing this, you're going to find the moment at both sides of each member. So MAB is 0.444 kilonewtons meter. MBA, how much MBA would be? Just look here. MAB, we discussed this, before, but it seems you forgot. What's the relationship between MAB and MBA? It's fixed from the bottom. There is no loads applied. There is no side sway. So what's the moments, the relationship between the moments? This is the previous example that we had here. And we said you're going to have this moment, just one half this moment. And we said, and as an approximate solution, you can just say that there is a hinge at 1/3 the height of the column, 1/3 height of the column, right? So the same here for member AB, there were no loads, okay? And there is no side sway. So if you find the moment here, this one's going to be double that moment, okay? How does this come? As you see here, MAB is 2EI divided by L theta B. This one is 4EI divided by L theta B. Just double that, okay? So MBA is 0.888 kilonewtons meter. MBC, how much is MBC? Without substituting back into the equations, how much MBC should be? Negative 0.888 kilonewtons meter. Why? Because we said MBA plus MBC has to be equal to 0, right? So if this one is 0.88, this one has to be negative 0.88 so that the summation is 0. And then MCB. MCB is 49.7 kilonewtons meter. MCD. Is there any relationship between MCB and MCD? For now, no. They are completely unrelated. So MCD is 6.18 kilonewtons meter. MCE, how much is MCE?
It's going to be negative whatever that is added together.
Yes, negative the summation of those, because those three have to add up to 0, right? So it's going to be negative 55.9 kilonewtons meter. And then the two other moments, MEC and MED, are zeros, right? So those are the moments now. So let's go ahead and try to draw the bending moment diagram here. So to draw the bending moment diagram, I'm just going to use those moments here to draw the free body diagram for each member. So here we have member AB, BC, CD, CE. MAB, let's see here. MAB was positive, so it's clockwise, 0.444 kilonewtons meter. MBA was positive, so it's in this direction, 0.888 kilonewtons meter. MBC was negative, so it's counterclockwise, 0.888 kilonewtons meter. MCB was positive, 49.7 kilonewtons meter. MCD over here was positive, 6.18 kilonewtons meter. MCE was negative, so it's counterclockwise, 55.9 kilonewtons meter. So what I'm doing here, I'm drawing the free body diagram, right? This is the free body diagram of each member. Member AB, BC, CD, and DE. Sorry, and CE. Is this free body diagram complete? No. What's left here? The loads that were applied here. Originally here we had 30 kilonewtons, and here we had a uniform load of how much? 50 kilonewtons per meter. Is this the complete free body diagram? It's not complete, okay? Why? Because there are some forces. Those are the moments. So in terms of the moments, those are correct. But there is a vertical force here, horizontal force, vertical force, horizontal force, and so on everywhere. Okay? So I'm not going to draw them, okay? Because actually, I don't need them unless I need to draw the normal force diagram or the shear force diagram. Here, I was not required to draw the shear force diagram or the bending or the normal force diagram, so I don't need those vertical and horizontal forces. I just need them in one member. Which one? BC. Why? Yes, to figure out how much is the moment at F here. Why do you need to find the moment at F? It's one of the critical points. We said to draw a correct bending moment diagram, you have to find the moment at all of the critical points. Point F here, you have a concentrated load. You have, if you don't find the moment at point F and you just draw the bending moment diagram, definitely it's going to be wrong, right? It's one of the critical points where the moment is going to change its slope. So you need to find the moment at that point F. So to find the moment at point F, okay, you need to pick your member at point F. So you need either this force or this vertical force. There are horizontal forces, but they have no effect on the moment at point F. Okay, so that's why I didn't draw them. There are horizontal forces, but I don't need them here. Okay, they're not gonna help me. Okay, do this. Okay, or finding the moment at point F. So now let's find those forces. So I can name this one. Let's say I will name this Y, the vertical force in the Y direction, at point C in member CB. So YCB. So I either need YCB or YBC to find the moment at point F. Okay? So to do this, I'm just going to take the moment, the summation of the moments at point B equal to 0 to find YCB. So what do we have here? Counterclockwise, let's say counterclockwise is positive, so negative 0.888. Counterclockwise is positive, so 0.888, and then negative 30 kilonewtons times 2.4, and the moment here, okay, that's negative 49.7 kilonewtons meter, and YCB is going to be positive YCB times 4.8 meters equal to 0. Right? So from this equation, you solve for YCB, it's going to be 25.17 kilonewtons meter. Just taking moment here, this one, plus the moment of this force, plus the moment of this force, plus the moment of this moment. Okay? and equated by 0, I found YCB. Now, how much is MF? How much is MF? When you calculate it from the left part of the right part? Definitely the right. Why? Because then I found YCB, okay? So just find it from here. If I try to find it from here, I need to find YBC. So Y have an extra step, okay? So YCB times this distance, okay? Minus the 49.7 kilonewtons meter. So MF is YCB, which is 25.17. This is kilonewton only, kilonewton, multiplied by 2.4 meters, minus 49.7 kilonewtons meter. So MF is going to be positive 10.71 kilonewtons meter. Now we can go ahead and draw the bending moment diagram. In this frame, okay, where you have an intermediate column, okay, this is the only time that I would, consider both answers correct, the direction of drawing the bending moment, okay, only for this member. So let's start now, drawing the bending moment diagram for each of those members, okay? Let's start with this very, very straightforward ones, okay? I want to draw the bending moment diagram for CE and BC and CE. So here. For BC, how much is MB? 0.888. When you draw it, would you draw it as a positive moment or a negative moment? It's negative moment, okay? Not because it's counterclockwise, it's because it's going downwards, okay? So the moment here is negative. What about the moment at point C? Positive or negative? It's going downwards, so it's negative, okay? MF was positive, okay? So let's draw those three moments here. So here you have negative 0.88. At point E you have positive 10.71. At point C, you have negative 49.7 kilonewtons meter, right? And what you do with those 3 points? Straight lines, because there are no loads. The moment changes linearly. And then, so it's negative here, positive, negative. Okay? What about member CE? You just draw or plot the moment at the critical points, which are MC and ME. How much is MC? 55.9. Positive or negative? Negative. Okay? So not because it's counterclockwise, but because it's going downwards. Okay? So negative 55.9. What about ME? 0. And now, how does the bending moment look like from point C to point E? Curve. So how to draw this curve? Will it go like this or like this? So to know this, we can have some hint here. If you connect the start to the end, okay? And then how would you draw your parabola? You come here, the midpoint, and then you go up with how much? W L square divided by 8. W is 50. L was how much? 6? 3.6. Right? 3.6 square divided by 8. Okay? So this becomes 81. Okay? Kilonewtons meter. What does this tell you? It's going to go to the positive because this is 0. This is 55.9. So this point is like, what, 27, right? Around 27.5. And then you go up by 81. So definitely this is going to be positive. Okay? Curve that looks like this. And it's negative here and positive here. So this is the bending moment diagram for those two members. Okay? And then we have the other two members here. Okay? Member AB. So let's start with the easier one. For member AB, how much is the moment here? 0.44. Positive or negative? Positive. This moment is positive or negative? Negative. Okay, so that's straightforward. When you look to this member from this side, you just turn your head like this. Okay, this is upward, this is downwards. Okay, so positive and negative. So this is positive. And this is negative. Then you connect them by straight line. It's going to be 0 at 1/3 the height here, so this is 0.444 kilonewtons meter, and here you have 0.888 kilonewtons meter. It's negative here and positive here. So if, for those three members, if you do anything other than this, it's wrong, okay? This is how you should get your bending moment diagram. The confusion here, okay, comes with member CD. The moment at point B is 0. The moment at point C, is it positive or negative? Negative or positive?
From inside.
Okay, so that's the problem here. How would you look for that member? If you look from this side, so that's positive, right? If you look from that side, so that's negative, okay? So here, this member, no, you have to look from inside the frame. So there is no confusion from this one. You should not look from here. This one also, this is, the bottom, this is the top. You have to look in this direction, this one as well. But this one, okay, there is no rule, okay? Especially if you had a column here. So would you look from here or from here? Right? You won't be able to do it, okay? So there is no problem, okay? But the thing is, okay, let's see now. If you look from this direction, okay, the only difference is the sign. But the way you're going to draw it is the same. Why? Because let's say you look from this direction. This is positive or negative? Positive, okay? So positive, you're going to draw it on the upper side, right? Where's the upper side? If you're looking from this direction, this is the upper side, right? So you're going to draw it like this. And how much is it? 6.18 kilonewtons meter. And then you're going to connect it by 0 here, right? Let's say you look from this side. Is it positive or negative? Okay. So if it's negative, which is the positive side and the negative side? If I'm looking from here, this is the positive, and this is the negative, right? So you're going to draw it in this direction, okay? Which we just did, right? So you have to draw it anyway. You look from this direction or this direction, you're going to draw it on this side. The only difference here that I will just allow you to do it is the sign. One of you is going to put it positive and one is going to put it negative. Okay? Both are correct. Okay? No problem here. Okay? You can say it's positive or negative, but it's in the same direction anyway. Okay? Any question here? So here, if you write negative, positive here, no, I'm going to subtract points, okay? But here, if you write positive or negative, both are correct. But you have to draw it on this side, okay? Any question here? So this is the bending moment. Yes? Did anyone say anything? Okay. So this is the bending moment diagram for this frame. So in this frame, we didn't have any side sway. Now, let's go ahead and try to solve some frame where we have a side sway. Okay? So now, example.
When you have different moments of inertia like that, you're going to give them to us, correct?
Yeah,
Like
definitely.
different members.
Yeah. Or sometimes I can give it like this. Let's say you have a frame that looks like this. I can tell you here, let's say, EI, 2EI, 3EI, 2EI, 2EI, for example. So what does this mean? It means that whatever moment of inertia is here, you have double it here, double it here, double it here, and triple it here. Okay? So that's actually easier for you to solve. Okay? So now, example 11.7. In example 11.7, we have a frame that we need to draw the bending moment diagram for it. And EI is constant. So EI doesn't change from one member to another. All the members have the same EI, the same moment of inertia, the same material. The frame looks like this. At this point, there is a concentrated force of 40 kips. And this is point A, B, C, D. Question now. Does this frame has a side sway or not? Can it have a side sway or not? It's only one of two things that prevent the side sway. Is it symmetric? No. Why not? Because you have 40K applied to point B to the right, there is nothing at point C. Even if there was something at point C, the frame doesn't look symmetric. The height or the length of the column at AB is not equal to the length of the column CD. It's totally unsymmetric, okay? So it's unsymmetric. Is there any support that prevents the upper level here, BC, from going to the left or the right? No. It's not like the previous problem, okay? So there is nothing preventing BC from moving horizontally. So there can be a side sway. So this frame, when it deforms, it can go like this. Okay? Have some side sway like this. So now we want to solve this problem. What's the first step? Break down the structure into individual members and find the kinematic degrees of freedom. A, B, B, C, C, D. Let's start writing the thetas, the rotations. Theta A. How much is theta A? 0. Theta B, unknown. How many theta B's? Just one. Both ends of member BA and BC share the same rotation, right? Theta C, it's just one rotation here. You don't have a pin connection between the two members, so theta B is the same, theta C is the same. What about theta D? 0. Now, for the delta, this is a vertical member, so delta is horizontal. Can point A move horizontally? No. What about point B? Can it move horizontally? Yes. So now point B can move like this. So delta B, this amount here, is the delta in this member. Do you know how much is this? No, it's unknown. So now, let's see now. For member BC, is there a delta? This is very, very important. This is one of the common mistakes I see on exams. Someone would say, yes, point B is going to move horizontally. Yes, but this is not the delta that we're looking for. Delta has to be perpendicular to the member. This is a horizontal member, so it has to be vertical displacement. Can point B move vertically? Can point C move vertically? So delta here is 0. For member CD, point D is fixed. It's not moving. Point C, can it move horizontally? How much? If it moves like this, how much? Do you know how much is this? No, I know how much is this. It's the same delta B. Why? Because this member, we're assuming it's going to remain the same length. It's not going to change its length. Axial deformation is prohibited. So if this moves delta B here, this is going to move the same magnitude, delta B. Now, if this is delta B here, this member, will it be delta B in this member or negative delta B? You remember we had this before in the beam. We said when you had two members, you remember when we had two members like this one, they are sharing the delta, okay? We said it's positive, or yeah, positive here, but it's negative here, right? What about those two members? Both are the same sign, because this one is going to rotate clockwise, so it's positive. This one is going to rotate clockwise, it's positive as well, okay? So they are rotating the same delta with the same sign, okay? Not opposite sign. So now, I just broke my member, like my frame, into those individual members. Now I need to find what are the kinematic degrees of freedom. How many kinematic degrees of freedom I have here? How many? 3 unknowns. What are those?
Theta B, theta C, delta B.
Theta B, theta C, and delta B. Those are my problem here, okay? Definitely I'm going to need to calculate those in this problem, okay? Those 3 unknowns. So now, let's move ahead to the second step, fixed end moments. And here, we're going to go to one of the common mistakes. What are the fixed end moments? Member AB, member BC, member CD. What's the fixed end moments for member CD? 0. What are the fixed end moments for member BC? 0. What's the fixed end moments for member AB? Is member AB loaded or not? The loads are the things that will give you a fixed end moment, right? So you have this 40K at point B, okay? So this would not be considered as a load at point B because it's just right at the end of the member. So it will not generate any fixed end moments in the member, okay? Will not generate any fixed end moments. Why? If you have a member like this, what are the fixed end moments? You assume that both ends are fixed, right? You have a load here, okay? This will not generate this moment. It's just going to go to this support right away. It will not generate any moments here. The moment is going to be 0, okay? So the fixed end moments are 0, okay? So this 40K, you just neglect it here, okay? It's right at the joint, so if it was a little bit here, it would give you some moment, okay? But since it's at the joint, no moment, okay? No fixed end moment. So for the fixed end moments, equals 0 for all members. No fixed end moments here. So now, what do you think about this problem? Just quick, that's why I guess, some students, they always want to have fixed end moment due to this 40K. What do you think here? If this small force is 40K, okay? Or if it's 80K, the bending moment diagram will be different, right? Definitely, if this is 40, if it becomes 80, the bending moment diagram will be multiplied by 2, right? So that's why, some students, they just want to put it in the equation, right? Now it's not going to be in the equation, right? When I write the slope deflection equation, nothing. It's not going to be there. Okay, that's fine. Don't panic, okay? There is no problem. The slope deflection equations. How many slope deflection equations we're going to write here? How many slope deflection equations? How many members do you have? 3. So you're going to write it 2 times for each member. Let's start with member AB. What's the slope deflection equations for member AB? You're going to write it twice. MAB and MBA. MAB is 4EI divided by L theta A. 0. Plus 2 EI divided by L. L was 12 feet. Theta B minus 6 EI divided by L squared, 12 feet squared. Delta, which is unknown, delta B, right? Remember, AB, it has a delta B, right? Plus the fixed end moment. How much is the fixed end moment? 0. So that's it, okay? Here we have, so this is in numbers here, this becomes 0.1667 EI theta B minus 0.0416 EI delta B. That's equation 1. MBA, 4EI divided by L theta B plus 2EI divided by L theta A, which is 0, minus 6EI divided by L squared delta B. Again, one of the common mistakes, okay? There's no excuse for you to do this on the test, okay? You say, okay, this is MAB and MBA, I'm going to put negative here and positive here. No, it's the same delta. It doesn't change the sign from one end of the member to another, okay? So this becomes 0.333 EI theta B minus 0.0416 EI delta B. That's equation 2. And then you go ahead to the next member, member BC, the horizontal member. And then I'm going to write the slope deflection equations, MBC and MCB. How much is MBC? 4 EI divided by L, which is 15 feet, theta B, plus 2 EI divided by L, theta C, minus 6 EI divided by L squared delta. How much is delta? Remember BC? 0, plus the fixed end moment, which is 0. So this becomes 0.267 EI theta B plus 0.133 EI theta C. That's equation 3. MCB, 4 EI divided by L theta C plus 2EI divided by L, theta B minus 6EI divided by L squared delta, which is 0, plus the fixed length moment, which is 0. So this becomes 0.267 EI theta C plus 0.133 EI theta B. And that's equation 4. And then you go ahead and write the slope deflection equations for the third member, MCD, the other column. Okay? So we're going to have MCD and MDC, both ends. MCD is 4EI divided by L. How much is the length of that column? 18. Theta C plus 2EI divided by L. Theta D. How much is theta D? 0. Minus 6EI divided by L squared. Delta. How much is delta? Delta B plus the fixed end moment, which is 0. So this becomes 0.222 EI theta C minus 0.0185 EI delta B. So that's equation 5. And then MDC, you have 4EI divided by L theta D plus 2 EI divided by L theta C, which is unknown, minus 6 EI divided by L squared delta plus the fixed L moment, which is 0. So this becomes 0.111 EI theta C minus 0.0185 EI delta B. And this is equation 6. What's the next step? Equations of equilibrium. What were your unknown ones? What are your unknowns? Theta B, theta C, and delta B. Theta B. If theta B is unknown, what does your equation of equilibrium look like? The summation of the moments about point B is equal to 0. If theta C is unknown, how would your equation of equilibrium look like? The summation of the moments at point C is equal to 0. Right? If delta is 0, B is unknown, so how would your equation of equilibrium look like? When you had a theta, it's a rotation, so moment is the equivalent force for a rotation. Delta is a linear motion, right? So actually you're going to have the summation of the horizontal force, the shear forces, equal to 0. At point B, is it at point B here? So I should put B here, right? No, this is a little bit different. Why? Because here, why did you say that the unknown is delta B? Why didn't you name it delta C? It's the same, right? So actually, the shear here, we're talking about the shear at that level. Okay? We're not talking about point B or point C. It's on this level because the delta is shared between those two parts. Okay? So it's the shear here. Okay? Okay? That has to be equal to 0. Right? So let's go ahead one step. First, does anyone think there is anything wrong here? There is something wrong here, okay? Okay, let's to clarify what's wrong here, I'm not going to tell you now. Let's draw the free body or the plot, the moments that we have, and try to understand how we're going to write our equations of equilibrium. Where do they come from? Let's write the free body diagram. Let's draw the free body diagram for those members. Here we have MAB, MBA, MBC, MCB, MCD, and MDC. The first equation of equilibrium, it says that the summation of the moments at point B is equal to 0. Those two moments has to be equal to 0, right? MBA plus MBC is equal to 0. Okay? So this is equation 1. The second equation of equilibrium, it says that the summation of the moments at point C has to be equal to 0. Those two moments has to be 0. That's easy, right? Those two equations are easy, okay? So MCB plus MCD is equal to 0. That's equation 2. The third equation, it says that the summation of the shear forces are equal to 0. Again, this is wrong. This is where the wrong part comes, okay? Now, if we draw the free body diagrams, we said you don't only have those moments, right? You also have horizontal and vertical forces, right? I don't draw them because I don't need them, but now I actually need them. Why? Because there is a horizontal force here. Let's name it, okay? VAB. There is a horizontal force here. VDC. There is an opposite one here. FVBA. And there is a one here. VCD. They are shear forces. Those are shear forces, right? Now, those two shear forces, VAB and VDC, how much are they? If you sum them up, how much should they be? 0? Okay, so one question here. Just remember what we did in structural analysis 1. If you study this, frame, and you say sigma fx equals 0, you have your frame like this, right? You have a horizontal force here, the reaction, right? Which we name it VAB. And you have this one, the reaction here, you name it VDC. Were there any other horizontal forces applied in this frame? 40 here. So now this is the wrong part. The shear force on this level is equal to 40, not equal to 0. Okay? So this is 40K. Okay? Here we have 40K. So what are those? According to the direction I just drew here, I need to have that VAB plus VDC equal to 0. You would say, now I'm adding those two shear forces. Those two shear forces are not at that level. Yeah, but VAB is equal to negative VBA and VDC is equal to negative VCB from the equilibrium of those two columns, right? The summation of the horizontal forces for each one of them has to be 0. Okay? Any question here? Okay, so next time I'm going to start from here, okay? How to calculate VAB and VDC. That's easy, okay? We did it before, but we're going to continue this next time. Just a quick note about your steam pitch competition. When you design your members, okay? Some not some, most of you, okay, you were assuming that you're going to connect the members. You're going to have a member like this and then another member like this. How are you going to connect them? Most of you said you're going to have like something like this, and then you bring it inside, and then you have male and female connection, right? That's fine, that's great, but please take into consideration that this will make your member longer. When you think about the length of the member, it's measured from here till the end, okay? And there is a limitation for the total length of the member of 3.5 feet, okay? So the total length, including whatever you're going to have here for the connection, has to be 3.5 feet, okay? Yes.
On our concrete test tomorrow, did you say we're bringing our ACI?
Yeah, you have to bring it.
Okay.
But just the ACI, no, the tables at the back of the book. You don't bring it, I'm not going to give it to you, okay? So, for example, let's say you want to calculate the area steel minimum, row minimum. You're not going to have the table at the back of the book. You have to open ACI code and look for the equation and write.
Okay.
Substitute the value. Let's say you want to use the tables at the back of the book for the, RN versus rho. Okay? You're not going to have the tables. You have to write the equation and substitute by yourself.
Okay.
Yeah.
That makes sense. All right. 'Cause I guess I wasn't understanding that email.
Yeah, you're not going to have that, but you'll be able to calculate that.
Okay.
That's on purpose. I want you to calculate it.
Okay.
Okay?